Okay, I think we should get started very soon. I have if you wish, write your name and contact information and interests in here. And Spanish is okay? I can read Spanish. Okay. Okay, so we're going to start with looking at longitudinal data, and then I'm going to talk about inference. So the data that I have are measurements on 888 subjects. And these are measurements taken on men between 14 and 17 when they start the survey. Let me get my pointer. But they're all started at different times. Yeah. So the data is collected on, these are all high school dropouts, so they left school before they got their graduate degree. It's part of a much larger study, the National Longitudinal Survey of Youth, that's conducted in the US on a sort of routine basis by the Bureau of Labor Statistics. And it's used in a book by Singer and Willett on modeling longitudinal data. And the information that we have, we've got a unique ID for each individual. We have their log of wages. Wages is skewed so that the log wages is just made automatically. Experience, this is the length of time in the workforce, and that ranges from about a year to 12 years. So they haven't studied them for a very long time. 12 years is about the amount of time that they have for them. And then some demographic variables, whether they got what's called a graduate equivalency diploma. And so if you don't finish high school in the US, you can sign up in some of the community colleges to get a graduate, the equivalent of a high school diploma in an accelerated form. So you can get that fairly quickly. Races, black, white, or Hispanic. The highest grade completed, so how many years did they complete? And then unemployment rate in the region. So every time a boy is measured, they also record the unemployment rate in the local region. So this one is a temporal covariate. These are all demographics specific to the individual. So to start with, so this is experience plotted horizontally and log wages plotted vertically. Let's stop this. Right, so the wages start out around $4 per hour, and the top amount is about $75 per hour. That's a lot, right? So $4 per hour is below minimum wage in the USA. 75 is a very nice amount of money to be making per hour. Yeah, and from 0 to 12 years. So some of the boys have only been measured for about a year, but many of them have been measured for 12 years. Okay, it's 888 is a fairly small data set. It's still very messy to look at in terms of plotting all the profiles, all the time profiles. So what I'm going to do is take the brush and just highlight cases. And it's good to think, what do I expect to see before you start exploring data? So with wages, what we expect to see is that wages increase the longer that you're in the workforce. All right, so we kind of expect that most of these boys are seeing an increase in their wages. By highlighting each case and just looking at the profiles, then we get some sense of what happens for an individual. So what happens for the individual experience. So question, does it look like the wages are steadily increasing over time? They're all over the map, right? So sometimes you see big changes in the wages that an individual gets. All right, so that's number one, and that was just achieved by brushing points in the edges, so just the edges. Maybe it's just the outliers we're seeing. So another way to look at it is just to take some random samples. So just random sampling of the profiles. So this is a view of, sorry, it's going to come pretty fast and I don't have the lines drawn, but this is a random sample of 50. Maybe that wasn't quite as extreme. Maybe we saw some profiles that were fairly flat. We saw, I think, one profile. Did you see the one that was fairly short but quite steady increase? But they were still fairly varied. Yeah. So, next one, let's look at some of the demographics. We sometimes hear that depending on your racial background, your wages are different. So I should stop this. They're just three, I think. I'm just going to show one group, another group, last group. Do you see a difference? No? Did somebody see any difference? Not so much, right? It doesn't look like that matters much. The primary variation in this data really seems to be the individual. Okay. Okay, another way to look at it. So let's take a look at, sorry, I'll just start this again. So let's just do some real simple statistics, fit a simple linear model separately for each person, right? Simple linear model separately for each person, and just take a look at that slope parameter. And then I'm going to show the profiles from the highest slope, maybe the top 50. So the top 50 increasing slopes. There's some. It's still quite varied. There's still a bit of volatility. I haven't taken account of smoothness, just looking at the overall slope. But there's still there are some steady increases, but there's still some large increases. All right, let's look and see. So there really are some boys that experience increasing wages over time. That's a good thing, right? Let's take a look and see if we can see boys that experience a decline in wages over time. That's the worst case. Right. There are some serious declines in the wages as well. Okay, so we're just getting a quick view of what's in the data, and let's look at modeling. Right, so a way to model this data is to use a linear mixed effects model, where we have fixed effects corresponding to the education. So this is highest grade completed, specifically laid out as factors. Race, whether they got a graduate equivalency degree. And then we also looked at some interactions between experience, length of time in the workforce, and other variables, but mostly they weren't present. So, and unemployment is included as a temporal covariate as well. And then subject is the random effects, right? So each we think of subjects, this is just a sample of 888 subjects, and so you think about those as random effects, right? Alrighty, and the model would say, I don't know, there's some significance. Experience is important. Unemployment rate actually is important, although the coefficient is minuscule, right? Highest grade achieved, at least if you get to 10th grade, 10th grade, there's a positive increase in wages, right? A little bit. And yeah, race didn't matter so much. At least these are just interaction. These are just the intercepts. So these are just vertical shifts. A graduate equivalency degree helps a little tiny bit to improve your wages. If you are black, then your slope changes. So the slope of the wages changes if you are black. All right, so that's the interaction between experience gives us a slope change ability. All right, that model would look like this. Primarily, it's the education and whether you're black or not, that might change your wage rate. But so these are those 4 categories in terms of the model. And if you just look at these lines, and this is what a lot of people really go on in terms of this data, say the longer you're in the workforce, the more you expect your wages to increase. On average, yeah, okay, on average that's true by this modeling. But look at the variation around that. And from what we did at the beginning, there's more to this data than that model. Right. So there's a lot more to this data than the model. Okay, so next. Next thing is, so we have fit a model. We also want to diagnose that model. Right? So it's good to have some understanding of the overall effect. But it's also good to see the fitted values for each person. All right, and so we want to now look at how well the model fit for each person. So this is my raw data here. And these lines are what the model would predict for each person. Okay. What do you notice to start with? So the scale is the same here. The scale's the same. The range, right? So the fitted model is a much smaller variation. And that's what happens when you use a random effects model. Basically, you're modeling by borrowing from other people. So essentially, you're shrinking everything to an overall average. And you can see that by looking at the fitted values here, that everybody's pulled towards the average. Right? Okay. One of the other things is we saw in the data that there were increasing and decreasing wages, and you would expect to see some increasing and decreasing wages in here. I think that in general makes a random effects model harder to fit when you've got slopes above and below, but no. Okay, so I'm going to sort these guys first by, I'm going to take the slopes from the fitted models and show the profiles for the individuals with decreasing wages. And we'll look at their raw data and we'll look at their fitted data. We want to roughly see whether they, how well they match, okay? I think this one's a pretty bad match. So this is the raw data, and it's a little volatile for that person, but generally it's a really steep decrease. That's a fitted model for that person. It's terrible, isn't it? It's just terrible. It's not the only one. So maybe this variation confuse things. But let's take a look at a few more. That's another one that's a fairly bad fit. Still volatile. It's given a very flat profile. This is the one that really bothers me. Very, very straight downward path for that person. And, sorry. Very, very straight downward path. I would expect that not to be messed up, but the fitted model is really quite flat. Okay, how does that happen? I think the model doesn't fit that well to each person. When you're using a random effects model, you really are borrowing information from other people, and that creates a very complex model fit. So you can get some very strange things like this. And by looking at each of the profiles, then we can work out, at least know about that. I don't know really how to fix it. But, yeah. Okay, so from that data, predominantly what we've learned is that it's an individual experience. So I don't think it's realistic to assume that your wages will increase over time. And it might be misleading for people to think that. Because certainly for these boys, that's not the predominant experience. The predominant experience is that their wages can bounce around a lot. So not to get too much expectation. So most of the boys do see some increase in wages. So once we have that we can summarize in terms of how many boys see increases or decreases. So some of them really see a decline. There's a small amount of difference if you're black, very, very small on average. It's still primarily you that matters more than anything else. And longer schooling does have a very small effect on the overall wages as well. Unemployment had little effect, at least for this data. Okay, any questions on that material? Alrighty, so I'm going to move on to inference. Okay, one of the things that we often associate graphics with is purely exploratory work. So it's not a test statistic associated with the plot of data. So it's hard to say whether a structure is statistically significant that you see or not. And that's been a big problem with graphics and exploratory work for a long time. So what we've been doing is primarily exploring. And I've been saying, well, I see this, but how do I make you believe me that I see that, right? Or maybe I'm seeing things that really aren't there. I'm just imagining things. So it would be nice to have an interplay between hypothesis testing and exploratory data analysis. And this is the connection for that. Okay, so this is a first example, just to motivate the problem. This is gene expression data, so that we have measurements. Well, here I've got, there's just 48 wasps that have been measured, but their gene expression for, I guess, 4 different types. So these colors are 4 different types of wasps, species of wasps. And for each wasp, we've done some gene expression. And what that means is that we have something like 6,000 measurements for each wasp. Yeah, wow. Which is the reason why it was reduced down to 40 to start with. Right, so we start off with 6,000 or more variables, and it's reduced to 40 variables. And so it's now 40-dimensional data with 48 samples. That's still high-dimensional compared to the sample size, right? But on that size of data, you can run linear discriminant analysis. If you try to run linear discriminant analysis on the full dimensionality, you don't have full rank of your variance-covariance matrix, and so you will have some problems. So here they've run linear discriminant analysis on this data. So they found the best 2-dimensional projection that separates these 4 classes. So this is a paper that was published in 2010. Is there a difference between the 4 classes? Yeah. So it looks like the 4 species of wasps have different genetic profiles. At least in terms of what they were studying, they had that difference on those particular gene expressions. Okay, so my question for you is, are you sure about that? All right, so here's a way to try to get some sense of whether what you saw is really in the data or whether it's just something you're imagining. The structure's pretty clear, but okay. There's a couple of new protocols that have got nice names, I think. The Rorschach protocol and the lineup protocol. Rorschach, probably people do this. If you've been involved in data analysis, you will do things like this anyway. Generate simulated data and compare that with your data. Or generate data under an assumption that there's nothing really happening in your data and look at lots of pictures of that. That's what the Rorschach is. The original Rorschach test, does anyone know what that is? Rogelio, do you want to explain it? In Spanish, you can explain in Spanish. Maybe.
Son muy conocidas, ¿no? Son figuras abstractas y tratan de te preguntan qué estás observando y son completamente abstractas y de ahí de las respuestas el analista deduce por qué estás enfermo. Psicología se utiliza mucho, supongo que sí, la verdad que no sé mucho.
Yeah, okay, so here what we're doing is generating lots of null plots and just seeing what can you see in those null plots. Because anything you can see in those null plots is just nothing. There's nothing there, okay. All right, the lineup protocol is different from that. This is you take your data and embed it in a field of null plots. It's just what we do with hypothesis testing, actually. It's the same as what we do with hypothesis testing. So, and the lineup, the name of a lineup comes from some meaning as well. At least in the US, sometimes the police, if they have a suspect, they'll create a lineup with that suspect in it. At least you see this on the crime shows all the time. So they'll have a police lineup with the suspect against other innocent people. And then they'll bring the victim in and ask them, do you recognize the suspect? And if they can recognize the suspect, that's evidence that that person was guilty. Okay. That's the same thing here. So if the plot of the data stands out as being different from the null plots, there's evidence for that data being different than the null, right? So if a person can detect the plot of the data versus any of the rest, that gives us some evidence that the structure in the data that we see is really there. Okay. So here's some Rorschach tests. So I'm just doing a side-by-side dot plot. And I've got two groups, group 1, group 2, and something measured here. And these are all just samples from actually an exponential distribution, small samples from an exponential distribution. Right, so you can see a little bit of difference there. I think there's no difference between the two groups. Wrong. Right, so just generating random samples. And anything that we saw there was just due to random sampling. This is the lineup. So now I've got 20 plots. One of them is the actual data plot, and the rest were generated, actually, I think, from permuting the labels of the data. So if there was an association or difference between the two groups, those two, that would have been broken. Can you see anything? These are tiny. I'll show you some bigger ones in a bit. You see any that are different from the others? Do any look different? So you're asked to pick one plot. Pick one plot that's the most different from the rest. Maybe that's too small to see, and the structure is not that big, but that's the actual data plot. I don't know, if you actually picked that, you picked out the data from the rest. But I haven't show you a small one. So that one, I know, is the data plot. You didn't know that, but okay. I mean, it does look a little different, right? So if you pick that without knowing, that says there's something different about that plot. Okay, the ideas are in this paper by Andreas Buya, and this is the Royal Society Philosophical Transactions, Series A. So Royal Society Philosophical Transactions, Series A. And that gives the basic ideas. Oh, yeah. Alrighty. And so all of the rest of these are null plots, and they were simply produced by each observation has a label, 1 or 2, and that label was scrambled. So basically, we think about putting all those labels in a hat and drawing them out of the hat. So if something was labeled number 1, it may have been labeled number 2 in the next, in the permutation. Right. Okay, so some brush up on hypothesis testing. When you're doing classical statistical inference, you start with a hypothesis. Right? You start with a hypothesis. It may be something like this. The null hypothesis is that the two means are equal, and the alternative hypothesis is that the two means are different. Okay. Then you collect data, and calculate a test statistic. The test statistic for that particular hypothesis would be typically the two-sample t-statistic. So it's the difference between the two sample means divided by a pooled standard deviation and by the square root of the sample sizes. And then you compare the value that you get from this with values from a sampling distribution. Right? And so for this problem, it's a t distribution with n plus n1 plus n2 minus 2 degrees of freedom, I think, although that can be a little bit dodgy, the degrees of freedom. So t distribution, if this value falls in the tails, either end of the tails, then it's considered extreme, right? So it's considered extreme, and you reject the null hypothesis. The rationale being that this distribution is calculated under the assumption that this is true, right? And so if what you observe is in the tails of that distribution, it says it's unlikely to occur if the null hypothesis is true. So that's evidence to say that maybe I don't believe the null hypothesis if it's in the extremes. Okay? Everyone's been through that before, right? The analogy with visual inference is quite similar. So you have a hypothesis, and it can be quite general to start with. So this is more specific than what we generally have when we're working with graphics. But for, say it's exactly the same case here, so same hypothesis, we make a plot of the data side-by-side dot plots. It's a really small sample, so dot plots are better when you've got a really tiny sample. The original data came from looking at some toxic waste site. They want to know whether they were cleaning them up properly. So this is our test statistic. The plot of the data is a test statistic. So it's not different really from all our other test statistics that we do. To make a plot can be a statistic as well. It's just a more complex sort of statistic. So it's not an average. It's a fairly complicated structure, but it's a test statistic. So take that test statistic and compare with values from the sampling distribution. So if I pulled values from a t distribution, I could do that. But this time I did the same as what I said before. I just take the labels and I permute the labels. Right. If the observed data is identifiable, that qualifies as a rejection of the null hypothesis. So you engage an independent observer, so you can't be your own test. You can't be your own judge. You need to get someone who has not seen the data and ask them whether there's one plot that's different from the rest. And if they identify the data plot, that's evidence against the null hypothesis. Right. We usually have this, is one of these plots unlike the other plot? And maybe some of you grew up with Sesame Street. Did anyone grow up with Sesame Street here? And they had this game for young kids, only 3 objects, where it was one of these things is not like the others. You remember that? Okay, well, it's a little bit like that game, but we have more to evaluate from. Right. Okay, in general, when you're making graphics, you don't have a firm hypothesis in mind. Right, but implicitly you do, because if you make a plot of your data, there's very specific reasons for making that type of plot. If I make side-by-side dot plots or side-by-side box plots, I'm interested in differences between those two groups. So implicitly, you have used a hypothesis. So this forces you to think about, what is my hypothesis underlying my exploration here? Okay. by using the data plot and by embedding it, having a mechanism that generates from the null, I can also catch multiple alternatives in a valid way. So I can account for there being all sorts of possible deviations from the null distribution in an organized way. One thing that people do, and I'll come back to that one. So one of the things you can think about is these 19 null plots